welcome to the first video in my linear algebra series. This series of videos is designed for those who are currently taking one of my linear algebra courses. However, I hope that if you're not in the course, you still find these videos to be helpful. In this first video, we're going to be introducing what matrices are, as well as looking at several operations for matrices. An m by n matrix is simply an array of real numbers that contains m rows and n columns. Right? So when you're looking at the size of a matrix, m by n, it's always number of rows by the number of columns. Written out, a matrix is represented in this way. So we'll say matrices are typically represented with a capital letter. A equals, right? And then the matrix, we have m rows, right? Row 1, row 2, blah, 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 row m. And then we have n columns, right? Column 1, column 2, blah, 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 column n. Each of these numbers, the A11, A12, blah, 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 blah. So each number aij, located in the ith row and the jth column of the matrix A, is called the ij entry of the matrix. So all of these numbers are called entries of the matrix. Right? We also write this here to represent a matrix, to represent the entire matrix. So instead of writing it out in this form up here for a lot of proofs, we'll represent it in this form. It's just a time saver, right? Instead of having to write an m by n matrix every time, we can just use this shorthand to represent it, right? So, for example, this right here is a 1 by 1 matrix, right? There's only one row and one column. This here is known as a 2 by 2 matrix. Let's try and move that cursor out of the way. Out here somewhere, there we go. This is a 2 by 2 matrix, right? You have two rows and you have two entries. Two columns, rather, right? For a total of 4 entries, right? So the 1, 1 entry would be 0, the 1, 2 entry is 0, the 2, 1 entry is 0, and the 2, 2 entry is 0. And down here we have a 2 by 3 matrix, right? We have 2 rows and we have 3 columns. Now we say that 2 matrices, so the matrices A and B, are equal. Oops. If they have the same size and their corresponding entries are all equal. Right? So the sum of two m by n matrices A and B is the m by n matrix A plus B, where the ij entry of A plus B is the sum of the ij entries of A and B. Right? So notice that in order for the sum of two matrices to be defined, right, the two matrices have to have the same size. Then, to determine each entry of this sum matrix, it's just the sum of the corresponding entries of the two matrices. For example, down here, the sum of these two matrices. First, we check. Right? The first matrix is 2 rows, 4 columns, 2 by 4. This is 2 rows, 4 columns, 2 by 4. They are both 2 by 4 matrices. And so the sum does exist and is also 2 by 4. And look, to determine each entry, right? 3 is the 1 plus 2. Right? Then we have 0 plus 0 is 0. Negative 1 plus 0 is negative 1. 2 plus 1 is 3. 2 plus 3 is 5. 4 plus 1 is 5. 0 plus 2 is 2. Negative 2 plus 1 is negative 1. Right? So it's basic arithmetic. You're just adding the corresponding entries, which will usually, at least in this course, be real numbers. Right? Numbers we're used to dealing with. Now look down here. Here we're going to try and add a 3 by 2 matrix to a 2 by 3 matrix. Those two matrices are not of the same size, and so that sum is undefined. Now, if we are given an m by n matrix A and some real number k, the scalar multiple of A by k is the n by n matrix, Ka, where the ij entry of k times A is k times the ij entry of A. In other words, to do scalar multiplication of a matrix, all we do is we multiply every single entry of the matrix by that scalar. Right? So for example, here we're multiplying a 4 by 2 matrix by the scalar 3. Right? And notice, all we do is we take each entry of the matrix multiplied by that 3. Right? So 3 times 3 is 9. 1 times 3 is 3. 2 times 3 is 6. 1 times 3 is 3. 1 times 3 is 3. 0 times 3 is 0. 2 times 3 is 6. 2 times 3 is 6. Now this also works in reverse. Right? So if you're given a matrix where every entry is a multiple of a scalar, you can then factor that scalar out. Right? So we can factor 3 out of this entire matrix. 9 divided by 3 would be 3. 3 divided by 3 would be 1, so on and so forth. The transpose of an m by n matrix A, where each entry is Aij, is the n by m matrix A to the t. This is read A transpose. We represent each entry Bij, where the ij entry Bij is equal to Aji. Notice all we did was switch the row index and the column index. Right? In other words, when you take the transpose of a matrix, rows become columns, columns become rows. For example, here we're given a 3 by 2 matrix, 4, 3, 0, 2, negative 1, 2. The transpose of this, B transpose, would be 2 by 3, where each row becomes a column. Right? So the first column of B transpose would be 4, 3. The second column would be 0, 2. The third column would be negative 1, 2. But look, it also works. The first row would be 4, 0, negative 1. The second row would be 3, 2, 2. So again, when you take the transpose of a matrix, all you do is you make each row of the original matrix the corresponding column of the transpose matrix. If we're given an m by n matrix A and an n by p matrix B, the product of A and B, or the matrix product, is an m by p matrix, A times B, where each entry, the ij entry of AB, is the sum from k equals 1 to p of the ik entry times, the ik entry of A times the kj entry of B. right? Where 1 is less than or equal to I less than or equal to M, and 1 less than or equal to J less than or equal to N. Now I know that for many of you this definition may be a little confusing, right? This definition will make a lot more sense when we actually take a matrix product. All right, so what we're going to do is we are going to take the product of matrix A and the matrix B given, and we'll also determine the size of A times B. All right. Now, there's one thing important to note. In order for a matrix product to be defined, the number of columns of the first matrix must equal the number of rows of the second matrix. And notice that the resulting size will be the number of rows of the first matrix by the number of columns of the second matrix. So down here, if we take a look at the size of A, it's a 3 by 2 matrix, isn't it? The size of B, it's 2 by 5. Right, so first ask, is this product even going to be defined? Well, the number of columns of A is equal to the number of rows of B. So this product will be defined. And the size of the product will be the number of rows of A, which is 3, by the number of columns of B, which is 5. So our resulting product will have a size of 3 by 5. Now let's actually take this product. All right, so A times B. We're going to have 2, 3, 0, 1, negative 1, 2, times negative 1, 4, 2, 0, 6, 1, 1, 0, 0, 3. All right. To determine the 1, 1 entry of our product, what we do, take the first row of A and the first column of B. Then we multiply corresponding entries. And when I say corresponding, I mean the first entry in the circle of A times the first entry in the circle of B, plus the second entry in the circle of A times the second entry in the circle of B. So we take 2 times negative 1 is negative 2. We're adding that to 3 times 1, which is 3. And we go along in this manner for every other entry. So for the next entry of that row, we now just look at the second column of B, still the first row of A. And we do the same thing. 2 times 4 is 8. We're going to add that to 3 times 1. All right, keep moving along. Two times 2 is 4. 3 times 0 is 0. Now this one is nice, right? Because we have a column entirely of zeros. So it's just going to be 0 plus 0. And then the final entry of the first row of our product, we get 2 times 6 plus 3 times 3. Now we move down to the second row. We'll take the second row of A, and we're going to do the exact same thing as we did for the first row. start by looking at the first column of B, and then we move along. Right, so 0 times -1 plus 1 times 1. I'm not going to continue to draw the circles. You should get the point. Right, 0 times 4 plus 1 times 1. 0 times 2 plus 1 times 0. 0 times 0 plus 1 times 0. 0 times 6 plus 1 times 3. And for the final row of the product, we now look at the third row of A, and we do the exact same thing. -1 times -1 plus 2 times 1. -1 times 4 plus 2 times 1. -1 times 2 plus 2 times 0. -1 times 0 plus 2 times 0. -1 times 6 plus 2 times 3. And now it's just a matter of actually doing this arithmetic. Right? So we'll have 1, 11, 4, 0, 21, 1, 1, 0, 0, 3, 3, -2, -2, 0, 0. This would be A times B. That concludes the first video in this series. The next video of the series will be looking at some properties of the matrix operations. It will be the first of many proof-heavy videos in this sequence of courses. So thank you all very much for watching this video, and I will see you all in the next one.